So I don't think a lot of you know me here, but I work at Scripps as a researcher, working in between CDIP and the Coastal Observing Research and Development Center, which focuses mainly in R&D work for observational techniques. I am very interested in extreme storm events, mostly in the form of extratropical and tropical cyclones, and collecting data so that we can look at these extreme events and try and piece together why there's always this bias in models not being able to predict or forecast the extreme events, often off by an order of a few meters. So a lot of work has been done with altimeter data to this effect. This is work done by myself and Trip Collins, looking at altimeter composites in a storm-centered reference frame, and looking at the bias and RMSE from hindcasts. And you can see regionally inside these storm reference frames, there's obviously some issues going on, so we need some more observations. Another example that I'm showing here is a CDIP bulletin that CDIP puts out when there's large swell events that impact our buoy array. So in each one of these panels, you can see that there's overshoot from the model, and this event is particularly interesting because it came from a long period swell from an extratropical system that occurred out in the North Pacific. And we can see that some of these model outputs are underestimating by quite a lot. So we're trying to look at observations in these extreme events in the generation sites, as well as what's happening from the generation site to the shorelines, to try and look at what's happening as the swell propagates over long distances as well. So I'm going to introduce a mini wave buoy data set inside this typhoon, and then the second half of the talk, I'm going to talk about swell propagating away from Typhoon Kanoon and how we're using some ray tracing to look at some of that data and compare it to some wave current interactions that we think might be happening there. So this is the mini wave buoy deployment that occurred on May 28th of this past summer. Some of our colleagues at the Applied Physics Lab at UW were kind enough to drop off these wave buoys for us. These are constructed in-house at our lab. And we dropped them off in what is known as Typhoon Alley, which turns out to be a great place to get some typhoon measurements. One, because it has very weak currents, so your buoys stay there for quite a while and just hang out in this chaotic eddy field. And it gives you a lot of opportunity to collect data from storms that are occurring there. So the mini wave buoy is your typical GPS-based wave buoy providing bulk statistics and directional wave spectrum, but the great thing is we're able to communicate with them and upsample or downsample them when storms are coming by. So that prolongs the battery life and lets us keep our buoys implemented for when storms are going to come and pass right through our buoy array. And over the next couple months after we deployed them, we had a series of storms pass through our array. And you can see when that happens, we can upsample the buoys. So I'm going to focus in on here, Typhoon Kanoon, when we got some good extreme measurements. So there you can see Typhoon Kanoon going through our buoy array, and you'll see flashes of the altimeter data available during this time period as well. And I'm just showing some scatter plots of the data relative to the distance away from the storm center here. And then the great thing about the buoys is obviously we have all this great spectra data to look at now. And there we go. So we got super lucky that it went straight through our array, and we have observations on both sides of the storm, which is pretty unique. And with all this great data, you can see the directions changing, and this is just direction calculated in each frequency bin using the A1 and B1 coefficients. And then as the storm gets further and further away, you can see the arrows here that are dominant wave period. Peak direction. And you can see these lower frequencies, we start to get these swell bands coming in from the northwest. So that's what we're actually going to focus in on the second half of this talk, and look at those currents, look at those waves going through currents and how they're affecting our buoy data. So we noticed after the peak of the storm, we get these HS oscillations away from the Array 5 nearest neighbor, and similar oscillations in the average period. So that is a classic signature of swell focusing by ocean currents. And we looked at the spectra data, and we could see that there's a big swell band of wave energy propagating exactly in that direction. So this is a really nice paper that I wanted to highlight because it's very relevant to this work, that ran Wave Watch 3 with and without currents for a typhoon in the Indian Ocean. And they found that compared to altimeter data, which shows this, again, oscillating power pattern of up to 1 to 2 meters oscillation, running the wave model with currents ended up in this same focusing pattern, and they did some ray tracing that also gave evidence of that in some realistic modeled currents. So that inspired us to do some ray tracing of our own. We have access to this WPOS Western Pacific Ocean State Estimate, which is run by my co-authors back at Scripps, Bruce Cornell and Ganesh Gopalakrishnan. And it's based on the MIT GCM, 1/6 degree resolution, 1 hour, and it 4D VAR assimilates SST and SSH from satellite, and takes initial conditions from HICOM and forcing fields from ERA 5. So it's a nice little wave current product that we can use for this. So our ray tracing setup just defines the source location in the southwest quadrant of the typhoon. So our typhoon would be right around here at this stage. And we define it as a line spanning diagonally across the southwest quadrant from 25 to 75 kilometers from the cyclone center, and a range of directions starting at 180 degrees straight south at the furthest point and closest to the storm, straight east. So that we cover our buoy array pretty well with rays. And you can see already from this animation that we have swell focusing bands from the refraction due to the currents. The nice thing about having drifting buoys is you have, current validation readily available. So you compare our buoy data to the velocity fields from WPOS and plot some rotary spectra and get pretty good signals that match up well between the model and the buoy, but you will see that the model doesn't actually have tides. But all in all, we're pretty happy with the agreement between the buoy-derived velocities in the model. So we decided to take this one step further and run a little ray density experiment. So at every time step, or every hourly time step along the hurricane track, we shoot rays of wave periods of 10 to 15 seconds on 1 second intervals to cover that swell band that we saw in the buoy data. And the source location is just going to travel along with the typhoon as it propagates to the northwest. And then we can bin these in time and space in 0.1 degree square bins. And we start to see some patterns of swell focusing in time. And if you focus on this buoy here, you'll see the swell focusing go in and out of that buoy region. And then compared to the mini wave buoy measurements to the ERA 5, you can see that when ERA 5 is underestimating these buoy measurements is times that we have increased ray density around our buoy. So that's a good indication that we have extra swell energy there from the refraction due to the currents. Just another quick example of another buoy showing the same thing. So you can watch the ray density wiggle in and out of this region, and it lines up well again with our pattern of significant wave height between buoy and ERA 5. And finally, we can do the same with an altimeter pass. And you see that it works well for these first two peaks in these regions here. But it kind of breaks down in the northern part of this which most likely means our very simple definition of source region and initial propagation direction probably isn't representative of what's actually reaching the points in the northern part of this domain. So just to sum up, we have a rich data set of upsampled mini wave buoy data in Typhoon Canoon. We have a lot more analysis planned aimed at informing the modeling of extreme wave events from this data. I would love to hear any suggestions from the modelers in the room that have definitely more intuition about what's going on in the models than I do. And from our relatively simple, not the most technical experiment using ray tracing from swell from Typhoon Canoon, we show the utility of these drifting mini wave buoy data, not only for wave measurements, but currents as well. And it seems like the scales responsible for refraction by these currents are well represented in our West Pacific Ocean state estimate. And with that, I'm happy to take your suggestions and answer any questions.